Early spacecraft systems, specifically on NASA's Gemini and Apollo missions, relied entirely on stored chemical consumables to keep their hardware running. Apollo's PEM fuel cells burned through stored hydrogen and oxygen to generate electricity and drinking water. This created a hard limit on mission duration. Once tanks ran dry, the spacecraft went dark. That engineering bottleneck was bypassed by replacing consumable power systems with high-efficiency, renewable solar arrays. A similar transition is transforming spacecraft propulsion, the systematic phase-out of our long-standing baseline fuel, hydrazine. Hydrazine is highly toxic and carcinogenic. Simply loading it into a spacecraft requires technicians to wear heavy scape suits and adhere to strict safety protocols. The hazards are severe enough that European REACH regulations are driving a complete ban on its use in aerospace applications. As an engineering baseline, however, hydrazine works well. It delivers a specific impulse of roughly 239 seconds, and it burns at a manageable flame temperature of 1170 Kelvin. While safety regulations force the phase-out, the actual engineering incentive to adopt green monopropellants is performance. These new chemistries provide the extreme volumetric efficiency required to build highly capable miniaturized spacecraft. This chart maps our analytical framework. We are plotting specific impulse on the y-axis against flame temperature on the x-axis, with the size of the bubble representing propellant density. Here is our baseline, hydrazine. Our first new chemical class is energetic ionic liquids, formulated by dissolving oxidizer salts into aqueous solutions and molecular fuels. When we plot EILs like AFM315E, their advantage is visible. They deliver a massive leap in volumetric specific impulse over the hydrazine baseline. With up to a 63% increase in density, spacecraft designers can pack more delta-V capability into significantly smaller propellant tanks. But look at the x-axis. That performance introduces a severe hardware constraint. EILs burn incredibly hot, often exceeding 2100 Kelvin. Containing combustion at that temperature without melting the thruster chamber is a complex material science problem. Engineers are forced to manufacture these thrusters from advanced, highly heat-resistant superalloys, like 3D-printed Ti64 or Inconel 625, just to survive the firing sequence. There is a secondary power trade-off. The catalyst beds required to ignite EILs demand significantly higher electrical preheating energy from the spacecraft before functioning. EILs force analysts to trade thermal simplicity and power efficiency in exchange for unmatched propellant density in volume-constrained satellites. The second class of green propellants is liquid NOx monopropellants. These typically combine nitrous oxide with hydrocarbons, like ethanol. Adding NOx blends to the performance chart reveals a highly competitive specific impulse, sitting well above hydrazine. Their defining physical advantage, however, is a vapor pressure of 5.2 megapascals, leading to autonomous self-pressurization within the tank. Most standard propellants require heavy, separate tanks of inert gas, like helium, simply to force the liquid into the engine. Because NOx blends push themselves out of the tank, engineers can strip entire inert gas pressurization systems from the spacecraft's architecture, saving profound mass and volume. The primary flaw, visible on the far right of the chart, is an extreme combustion temperature exceeding 3000 Kelvin. Beyond the heat, storing a pre-mixed oxidizer and fuel in a single, highly pressurized tank introduces severe operational risks. Chief among them is the constant threat of catastrophic flashback. To prevent combustion waves from traveling upstream and detonating the main tank, designers must integrate mandatory hardware additions, like flashback arresters. NOx blends sacrifice deep combustion stability and thermal safety to radically simplify a spacecraft's internal plumbing and feed architecture. The third and oldest green chemical class is hydrogen peroxide aqueous solutions, utilized specifically at high-test peroxide, or HTP, concentrations. Plotting HTP on the chart plainly reveals a specific impulse deficit compared to the hydrazine baseline. Propulsion analysts deliberately choose a chemical that yields a 20% performance penalty for specific modern mission profiles. They accept that penalty because HTP has the chemical capability to achieve hypergolic ignition when paired with specific green ionic liquids or hydrocarbons. Hypergolic ignition triggers immediate, spontaneous combustion upon contact. This eliminates the need for heavy catalyst beds or electronic igniters. The moment these two distinct liquid streams collide in a combustion chamber, a violent, instantaneous energy release occurs. This property allows HTP to serve a dual role. It can decompose independently as a monopropellant for small attitude control thrusters, while simultaneously serving as the oxidizer for the main engines. Hydrogen peroxide forces analysts to trade pure specific impulse for architectural flexibility, high ignition reliability, and system-wide mass reduction. The ultimate beneficiary of these dense, highly specialized green propellant chemistries is the modern CubeSat. Historically, small satellites lacked the volume to house both a high-thrust chemical system and a high-efficiency electric system simultaneously. State-of-the-art green propellants make the breakthrough concept of multi-mode propulsion entirely possible. This schematic shows the internal architecture of a multi-mode system. A single shared propellant tank routes fluid to distinct mechanisms. The first path leads to a chemical thruster for rapid orbital maneuvers. A parallel path flows to an electric unit for highly efficient station keeping. Achieving both propulsion modes within the same footprint represents a significant reduction in hardware overhead for spacecraft designers. Furthermore, cutting-edge proprietary propellants like GEM or green electric monopropellant can be electrically ignited, bypassing the need for heavy catalyst beds entirely. This enables the continuous high-efficiency operation of a liquid-pulsed plasma thruster, utilizing these advanced chemistries in a total vacuum. Compare this streamlined single-tank multi-mode system to the bloated dual-tank architectures required during the Hydrazine era. Mastering the thermo-chemical trade-offs between EILs, NOx blends, and hydrogen peroxide is the only way analysts can optimize these complex architectures. These chemistries serve as the foundational technology for the high-density, multi-role propulsion systems required for the next generation of spaceflight.